Okay, welcome to lecture here. Again, we're going to lecture here on chapter 14. We'll continue on. And then, as we talked about last time in the announcement, we'll take the quiz at the start of lab. And then, obviously, we'll do something afterwards for the rest of the time. Okay, so we've been talking about chapter 14. And chapter 14 is about acids and bases. We talked about, again, some definitions of acids and bases. Bronsted-Lowry definition, which is often sort of the definition that most people sort of think about when they're talking about acids and bases. An acid being a proton donor, so something that gives away an H+, while a base is something that will accept that H+. And that creates those acid conjugate base pairs that we talked about, where essentially the only difference between everybody is one H+ difference. So in order for an acid and its partner on the other side of the equation, which is the conjugate base, should only have a difference of one H+. Remember, the plus part of that does affect the charge on those things, especially when we're talking about conjugate acids and conjugate bases. And then the base and its partner on the other side, which is the conjugate acid, also just really the difference of one H+. The idea there is basically the acid will give away the H+, and the base is accepting the H+. And again, that's why basically the only difference that you could have when you have those two things, again, is that one H+. As we talked about last time, again, on the left-hand side of the arrow where our reactants typically are, that's where we find sort of our regular, if you want to think about it, it's just regular old acid and bases, who's going to be sort of accepting and donating. On the product side is typically where we find our conjugate acids and conjugate bases. And again, those are basically the results of that sort of transfer. We also talked about the pH scale, which is a measure of acidity, runs from 0 to 7 and to 14. Below 7 is acidic, above 7 is basic. Right there on 7 there is neutral. And as you go from, say, 7 towards 0, it does become more acidic. As you go from 7 towards 14, it becomes more basic. To calculate the pH, that's the minus the log of the H+ concentration. We also talked about a similar scale, which is the pOH. And the pOH runs opposite of the pH scale. So if you have a low pH, you have a high pOH and vice versa. But to calculate the pOH, you take minus the log of the OH minus concentration. And really the nice thing about that is if you take the pH and the pOH and add them together, it equals 14. So that gives you a little variety in terms of how you could solve certain problems. Could also use something like Kw that we also talked about, which is the H+ concentration times the OH minus concentration will equal 1 times 10 to minus 14. And obviously knowing which one is larger, the H+ or the OH minus concentration, will allow you to figure if it's acidic, basic, or neutral. The H+ concentration being pretty much the acidic part of the solution, OH minus being the basic part of the solution. We also, towards the end as well, talked about two other ways you could sort of get those concentrations, the H+ or the OH minus concentration. So if you were given the pH value, you could get the H+ concentration from that by taking the inverse log of the minus pH. So remember, that's the one when you hit on your calculator, usually will pop up a 10 and a caret, and make sure you make it negative. And if you have the pOH, you could get the OH minus concentration. Pretty much identical calculation. You're going to take the inverse log of the minus pOH. Again, a 10 and a caret usually will pop up there on the calculator when you hit that. And a couple other important things that we also talked about. H+ and H3O+ are basically equivalent to each other. So again, they're interchangeable both in formulas and sort of reactions as well. And most importantly, with all this stuff, you definitely want to be making sure that you are using your exponent button, which is that EE button, that EXP button, when you're typing these numbers in. Otherwise, you will find yourself off, especially now that we're doing things with obviously logs, maybe inverse logs and stuff like that. Any questions on any of that stuff we talked about, I think, last time? Okay, so we did some examples before, so I think this is where we laid up here. So another one here. So take a minute or two here, and what we're looking for is pretty much everything. So what's the pH, POH, and OH minus for this particular solution as an H plus concentration of 3.5 times 10 to the minus 6. And obviously, while we're at it, why don't we also add, is it acidic, basic, or neutral here? So acidic, basic, or neutral. All right, so take a couple of minutes there, see what you come up with, then we'll talk about it there. A good review of everything we just talked about. A variety of ways you could maybe solve this, depending on sort of which path you choose. But since we do have the H plus given to us, we can go, one of the things we could do right off is go directly into, obviously, the pH equation, which is our minus the log of our H plus. So that would give us minus the log 3.5 times 10 to the minus 6. And that looks like, looks like 5.46 there. Looks like as our pH value. Again, a reminder that this guy has two significant figures. That translates to not two sig figs here, but again, two decimal places when we go to the pH. We could then, one thing, we could get the POH by simply subtracting 14 at this point. So that would be 14 minus our pH value. That's going to give us 14 minus 5.46. And that looks like perhaps we will end up with 854 as our POH value. And now really you do have the same kind of two options at this point, or a couple of options to get the OH minus concentration. We could take the inverse log of the minus POH. Again, that OH there is going to allow us to get to it. Again, on your calculator, that probably will pop up like a 10 and a caret. You want to make sure you go negative on that, not the subtract button. 8.54 looks like what we want to go with there. And looks like maybe. Looks like, again, your calculator might cut you off there. Mine did. I had a bunch of zeros and a 3 at the end. But if you kind of put it in scientific notation, you'll end up with something like 2.9 times 10 to the minus 9. And that would be molar. And again, if your calculator is not in scientific notation, you probably had a ton of zeros and like a 3 at the very end, and it probably just rounded for you and stuff like that. So that's how we get that 2.9 times 10 to the minus 9. Lastly here, we want to know, is it acidic, basic, or neutral? So remember, we also talked about this last time, that answer is just one answer, and you should always look at the pH value, as that's usually the scale you have in your head. And when we look at our pH value here, it is less than 7, which means this guy here should be acidic. Any questions on any of those calculations, where we got any of the numbers from or anything like that? Okay, so again, clearly you need to be able to calculate all these things, the pH, the POH, H plus concentration, or OH minus concentration. Also, again, a reminder, you could have, if you wanted to, for the bottom there, you could have done the 1 times 10 to the minus 14 right off the bat as well, or at some point divided by 3.5 times 10 to the minus 6. And that should have hopefully got you there as well. So again, that's the alternative way you can do that, using KW to get there. Any questions on any of that? Okay. Then rolling along here, let's talk a little bit about acid and bases in terms of electrolytes. So just a couple reminders. An electrolyte is pretty much a substance that when it goes for a swim there in a solution will break apart into ions. Because those ions are present, it's able to conduct electricity. So there's strong electrolytes, there's weak electrolytes, and then there's pretty much non-electrolytes, which do dissolve but do not conduct electricity. So an example of a strong electrolyte you might remember is sodium chloride. You put it in some water, and then pretty much what you have is a sodium chloride solution. But really what you have floating around in that solution is 100% pretty much these ions that are floating around. Perhaps you might also remember a lot of times they do something with like a light bulb. So the light bulb would go off very, very brightly here if you put it into a sodium chloride solution, because of the presence of all those ions, helps kind of complete everything and conduct electricity really, really well. Now, there's also weak electrolytes, and weak electrolytes are also found with, weak acids, and there's also weak bases as well. And unlike sort of a strong electrolyte, pretty much what you got here, this is acetic acid, by the way, pretty much what you have in solution is mainly the whole thing together. You will produce, though, a few of these ions. And that's why it's typically these kind of reversible reactions we've been talking about involve these weak electrolytes. Again, because it's still able to produce a few ions in solution, it's still technically considered an electrolyte. It can still conduct electricity. It will not conduct electricity anywhere near a strong electrolyte. In cases of an acid or base, we do have strong acids, which are essentially strong electrolytes. We also have strong bases, which are also strong electrolytes. And again, we also have weak acids and weak bases, which basically follow the more weak electrolyte approach. Some of the strong acids that we probably have talked about here before. Here's some of them: hydrochloric acid, we got nitric acid, we got perchloric acid, we have some sulfuric acid happening there. These are all pretty much strong electrolytes, which pretty much means 100% of kind of everything we got going on is on the product side. We have none of, say, an HCl unit still present in solution, no nitric acid, no perchloric acid, no sulfuric acid. Again, it pretty much 100% sort of dissociates. Other strong acids, HBr is a strong acid, hydrobromic acid, hydriodic acid, also a strong acid. So those are some common examples of some strong acids here. This is also another way you could write this. So in each of these sort of equations, as we talked about a little bit earlier in this chapter, these are all really just the acid breaking apart in solution. And if you write it here with the water in the reaction, that is how we produce H3O plus. And a reminder that you could also represent this by just writing something like HCl going to H plus and Cl minus. So again, this equation I just wrote is basically the same as this equation here. Only difference is the one on the from the slide had water in it. That's why we produce H3O plus. If you decide not to include water in it, which is perfectly fine, you won't get H3O plus on the product side. You'll get H plus. And again, these guys are essentially the same. Any questions on that there? Now, weak acids, as we talked about before, these are some examples of some weak acids, but they're all weak electrolytes, which means they are going to go, again, back and forth in that reversible sort of reaction. The difference is, again, a weak acid versus our strong acid is they are going to mainly stay together. So something like hydrofluoric acid here is mainly going to stay together. We'll produce a little bit of these ions, but mainly be hanging out kind of in this direction here. That's nitrous acid and so forth coming through. These are also really just equations to show the acid breaking apart into its ions. In this case, they did include the water in each of these. And again, that's why we see the H3O plus. You could just as simply, just like the strong acid for a weak acid, also not include the water in the dissociation equation and just write it as H plus and F minus. And again, these two equations are the same. This H plus here, again, is the same as the H3O plus here. And they're both perfectly fine ways or okay ways of representing sort of what's happening here in that reaction. And it really is sort of your call as to, how you want to do it. Like I mentioned before, and like you probably have been seeing, I personally will kind of go with this approach for it and not really include the water. But it's nothing wrong with including the water and getting the H3O plus on the product side. In terms of bases, we do have strong bases. These are strong electrolytes, which also mean that they 100% break apart. So we take some sodium hydroxide, potassium hydroxide, barium hydroxide, and much like our strong acids, we 100% have our ions in solution. They completely break apart, and again, very good conductors of heat and electricity. A lot of really strong bases, a lot of strong bases do actually contain that hydroxide in it. And I think I might have mentioned it the other day, but if you look on the periodic table there, group 1, where sodium is, potassium, hang a right, take like calcium, strontium, and barium. These guys there on group 1 and 2 of the periodic table, which is our alkaline metals, our alkaline earth metals. These are guys, when they have hydroxide, are a lot of where our strong bases come from. And again, alkaline means basic. So hence the name of those two groups basically have some form of alkaline in it. And again, that's where a lot of our kind of strong bases come from. As we also talked about previously as well, not all bases, will contain hydroxide. And there are certain bases that actually don't have hydroxide in them, but can produce hydroxide, and they're still considered bases. So there are some weak bases usually in that situation. So here's a couple of examples for weak bases. F minus, NO2 minus, NH3 is also a weak base, right? Plus some water. Again, acting as a base, going to accept that H plus. And when it does so, you get NH4 plus and a little OH minus. So all these guys, they do produce OH minus on our product side. So, that oftentimes is kind of going to indicate more of a base sort of situation, as opposed to if you look back on sort of the acids there. On the acid, we do see on this product side H plus or H3O plus, more of an acid sort of situation occurring in those particular cases. So sometimes people, and we'll talk about this in this chapter a little bit more, always wonder like, am I dealing with an acid? I'm dealing with a base. Should I be using sort of an acid number or a base number? And again, that's a very simple way to usually be correct in those sort of assumptions. If you look on the product side and you see OH minus, you're probably doing something that involves bases. If you look on the product side of the equation there and you see something like H plus or H3O plus, you're probably doing something that involves sort of an acid situation. And that's why it's really important in this class, as we talked about as well, to know how to properly write these equations so that you get the correct products on the equation, and it'll also help you with the calculation part of it. The other thing I will say in terms of sort of including water in sort of the reaction, this is usually a good place to actually include the water when you're writing equations, especially for weak bases, because very often people can't visualize what's going on. So having that water there and knowing it's probably going to act as the acid and donate the H plus, it's a good thing to kind of include in those weak base sort of equations. Again, in the acid, it's your call if you want to do that, but the base one, you should probably do that because people struggle sometimes with sort of what's going on. Any questions on that there? Also, a really important sort of relationship is pretty much what we see here in the top there. The conjugate base of a strong acid has no measurable sort of strength. So, our relationship, if you remember, is we have basically an acid and a base on the left-hand side. We have our conjugate acid and our conjugate base on the right-hand side. And again, these guys are related to each other, and also in a relationship probably, I guess. And we'll go that way as well. But so the relationship between those two is, if the acid was a strong acid, that means its partner on the other side will be relatively weak. And vice versa, if the acid you are starting with on the left-hand side is relatively weak, its partner on the other side will be relatively strong. So there's sort of an opposite relationship that occurs with the acid and its conjugate base, and also the base and its conjugate acid as well. So if your base on the left-hand side is weak, your conjugate acid will be relatively strong. And the same thing holds if you're starting with a strong base on the left-hand side there. Its partner on the other side will be relatively weak. And that's going to be really important, especially towards the end of this chapter when we talk about what happens. When we talk about the conjugate partner being strong, we're not talking about it being strong in the sense as strong as, say, a strong acid or strong base. But what we're talking about in terms of it being strong is it has the ability in certain situations to actually continue to react. And so that's a very important sort of conceptual understanding to help you understand calculations coming up and stuff like that. So again, when we say it's strong, doesn't mean it's strong like a strong acid, but it's strong in the sense basically it has the ability to continue to react. And what we'll see it usually react with is something like water. So sometimes when we produce these sort of conjugate acids or conjugate bases, because they're relatively strong, they will continue to react with water and have an effect on whether or not that solution will end up being acidic or basic. And we'll see that a little bit later on this chapter when we talk about salts. In terms of just sort of the strongest acid that can exist is H3O plus and OH minus. And again, that's sort of what we use to determine if it's acidic or basic toward a solution. Here's sort of a table, not from your book, but you have a similar one that again talks about some of those strong acids we see. And if you look at sort of the relationship on the other side, we see that opposite relationship, sort of our strong acids over here, their partners are relatively weak on this side, while as we come down this way where we get our weak acids, their conjugate bases on this side will be relatively sort of strong. So that opposite sort of relationship basically occurs with our partners there. And again, this just graphically shows you what we talked about. Strong acid or base 100% breaks apart. Anything weak pretty much going to stay together, but still able to generate either H plus or OH minus, which makes it a weak acid or a base in that particular case. So why don't you take a second here and figure out what is the pH of each of these solutions here and see what you come up with, and we'll talk about it. We're given what is the pH of 2 times 10 to minus 3 molar HNO3 is nitric acid. So in this case, we don't have just a generic sort of H plus, H3O plus, or OH minus given to us, but we're actually given a formula, and we should be able to recognize that as a strong acid. And because nitric acid is a strong acid, it's going to 100% break apart into H plus and NO3 minus. So, you know, what you have floating around in that solution is 100% what we got on our product side. In terms of the pH, really the only thing we're concerned about is the H plus concentration, because that's really what we need to calculate our pH. And since the whole thing here is 2 times 10 to the minus 3 molar, it is a 1-to-1 relationship between the H plus concentration and the nitric acid, which means we know that the H plus concentration should be 2 times 10 to the minus 3. And that's really all we need here to go into our pH, which would be minus the log of our H plus concentration, giving us minus the log of 2 times 10 to the minus 3. And that's going to get us minus log 2 to the, not that button, minus 3 there. And it looks like 2.7 as our pH. You may be wondering again why maybe I went to just one decimal place, and it's because this number here has one significant figure. One decimal place here would be 2.7. First off, questions on the calculation there. This also would be acidic, right? Didn't ask, but this would be an acidic solution, as again, our pH is 2.7. Also didn't ask if we want the POH, we could have subtracted 14 from it and so forth. So let's take a look then at the bottom one there, which is 1.8 times 10 to the minus 2 barium hydroxide. This is definitely not an acid. I see hydroxide, group 2, probably a strong base in this case, which means this barium hydroxide, when it goes there for a swim, is going to 100% break apart into barium ions and a couple of hydroxide ions in this case. Again, 100%. This is what we should have going on in solution. In this particular case, since we want to get to the pH, it would probably make sense to first go to the pOH, which means we need minus the log of the OH minus concentration. That means really the OH minus concentration is the important thing here. Different in this case, though, is the barium hydroxide. I'll write up here. Barium hydroxide is 1.8 times 10 to the minus 2 molar. But when we look at the hydroxide on the other side, it is not a 1-to-1 relationship, but it is a 1-to-2 relationship, which means we do need to adjust it by multiplying by 2 times 1.8 times 10 to the minus 2 to get the proper concentration of our hydroxide. And that would be 2 times 1.8, wrong button, try that again, 1.8 minus 2, looks like something like 0.036 molar. And that is really what we want to go into here with. And that would get us an error, apparently. That will get us, if I hit the right button, maybe, that will get us 1.44, looks like, perhaps, as our pOH. Again, not the answer because we are looking for the pH. So the pH would then be 14 minus our pOH. That's going to be 14 minus 1.44. And looks like a 1256 on the pH there. That pH of 12.56 would tell us that it is basic, which we would hope because it is a base. So that does make sense. If you stopped at the pOH of 1.44 and thought it was the pH, that shouldn't make sense to you because that would be an acidic pH if you thought that was the pH. Question on any of those steps there? All right, so dealing with strong acids or strong bases and calculating the pH is not too difficult, again, because they are strong. They 100% break apart. So pretty much all you need to determine is either what is the H plus concentration or what is the OH minus concentration to calculate either the pH or the pOH. One question was, where did the 14 come from? The 14 came from that relationship that we saw the other day as well, which is if you take the pH plus the pOH, it equals 14. So in this particular case, we had the pOH we calculated, so that allowed us to rearrange it to get to 14 minus the pOH in this particular case. Yeah. Other questions on that? Okay. All right, so that would be nice if everything was, pretty straightforward like that, but obviously it's not going to be. So when we deal with weak acids and also weak bases, we'll talk about, it's a little bit more difficult, or a little bit more, I won't say difficult, it could be, I guess, but a little bit more steps involved to get us to the pH or the pH. And that's really because when we're dealing with weak acids or weak bases, they do not 100% break apart into, say, H plus or OH minus like we have here. It's a back and forth, which means, we get only a little bit perhaps of H plus or OH minus that's actually free in solutions. So if we write sort of a weak acid, and this, by the way, is a generic formula for a weak acid. That's a weak monoprotic acid. Monoprotic means it's got one H plus to give. So that's kind of like a generic formula you can use for that, HA. By the way, diprotic acid means that it has two H's it could give away, which is that. And a triprotic acid has three H's pluses it could give away. So that's kind of a generic formula for that guy as well. So when you see HA, it's just really like a generic sort of formula for a weak acid, you know, something like say HF or something of that nature. The A is the anion basically. And remember what makes something an acid is basically H plus is the cation. So again, here the A would be A minus. The A here would actually have a 2 minus charge, and the A here would actually have a 3 minus charge when you look at these sort of generic formulas. So if we write sort of the dissociation of our weak acid, which again, oftentimes could be represented by something like this, we do see our reversible reaction happening. And our reversible reaction means it will set up equilibrium. Equilibrium means we could write an equilibrium expression as we see here. And that is the same equilibrium expression that we've been talking about. It is our products over our reactants. If you were to use this equation here, just like we talked about with equilibrium, this would not be included in the expression because it's a pure liquid. So you would end up with, if you wrote the Ka value there, or expression for the top equation, it would look something like this, very similar to the bottom one, except obviously no water in it. And instead of H plus, you have H3O plus. So this expression and this expression, same deal. They're equivalent to each other as well. So it's an equilibrium expressed for a weak acid, hence the A here, Ka value. Ka values is really the acid ionization constant or dissociation constant. As the Ka value increases, the strength of the weak acid increases as well. So the higher the Ka value, the stronger the weak acid it is. Again, it's still a weak acid, which means it is not stronger than a strong acid. It's just a strong weak acid, if that sort of makes sense there. And why is that? It's really the same sort of idea as what we talked about with basic equilibrium. If I have a large value of K, that means when I reach equilibrium, I mainly have products present. And if we look at our sort of equation here, if I have mainly products when I reach equilibrium, that means I have a lot of free H plus. And that's really what makes something an acid, is the free H plus, right? So the presence of free H plus is what makes something really sort of acidic. And it's also the presence of free OH minus that makes something basic. So if we have a large Ka value or larger, higher Ka value, that means, again, it is a stronger weak acid in comparison to another weak acid. Any questions on that? Would we find perhaps a Ka value for a strong acid? And the answer is no, you would not actually. And the reason for that is if we have a strong acid, it is a 100% one-way arrow where everybody is breaking apart into ions on our product side. You have nobody coming back. There's no like HCl units in there. And because there is no back and forth reversible reaction, you can't have an equilibrium constant for it. So this is a very good way as well, one of those kind of like hint type things as you go through problems. If you see a Ka value associated with an acid, it's a weak acid. Yeah. So, you know, if you see it in the problem, you can find a Ka value on the table. It's a really good way to know that obviously it's a weak acid and stuff like that. Again, strong acids will not have Ka values associated with them because they don't set up that equilibrium. So that's a good way. You know, as soon as you see that Ka value, you should go into, this is weak acid mode. This is probably going to be ice tables, as we'll talk about here in just a second. And that's where we're going to go with it. The only one that you might potentially see considered a strong acid on a Ka table is H2SO4, which is sulfuric acid. And they usually will not give you a pretty good value for that first one. It'll say something like it's very large, which obviously is not a very helpful value or something like that. And it's only on there because it's a diprotic acid. So when something, say like sulfuric acid, breaks apart, those H's do come off one at a time, which I think we might have talked about as well. And really, for the most part, it is, you know, sort of this part of it, the second H that comes off is really weak. This part is really considered more of a strong acid heading in one direction. But when you get this guy involved here, the HSO4 minus, it does behave more like a weak acid. So out of all the strong acids, that's probably the only one that you'll ever see maybe even listed on the table. And usually when it's listed on the table, like I said, they give you something like it's a really big number, which is obviously not helpful. So since it's a really big number, it's pretty much considered a strong acid. But again, here, as you can see, even on this table here, you do find it's sort of second H plus that would come off as more of a weak acid and found on that table. Here's a list of some weak acids. Here's the Ka values. And again, you can see as the Ka value gets higher, the acid is more stronger. And again, that's because pretty much you would have more free H plus sort of produced on that end. You would have less H plus sort of produced in theory on this end as you come down through there. Obviously, these values would be provided to you. You may have to look them up for certain things, you know, and say book problems or something like that, but quiz, exam, or something like that, it would definitely be obviously provided for you. So let us take a look at one here together, how we approach a sort of weak acid type of problem here. And we want to calculate the pH of a 0.5 molar HF solution. So because we would be able to look it up and see that it has a Ka value of 7.1 times 10 to the minus 4, we automatically know it's a weak acid. And pretty much the way we approach weak acid sort of problems is we essentially just pretty much do ice tables. And we do it exactly the same way that we did sort of ice tables in the previous chapter. The only real difference is at the end, instead of usually being interested in what is everybody's concentration when we reach equilibrium, we're really interested in the pH. So really the main thing in most of these calculations is we need to get to the equilibrium line and figure out what is that H plus concentration once we actually reach equilibrium. Because what that will tell us is essentially in that solution, how much of that H plus is basically freely floating around. And because really pH is based off of the amount of free H plus, that's ultimately here. We always, in most cases, are looking for what is that guy's concentration at equilibrium. So we started pretty much identical to, you know, how we would approach it normally. We would just take our equation. We'll do an ice table here. And very much like a lot of the assumptions that we make in a normal sort of one, we're only given information about HF. So that's all we'll put here. I'll even add an extra 0. I think there's supposed to be a 0 there. We'll put it there. And because we weren't given any information about our products, just like in we did last chapter, we'll assume that it is 0. Also, because we weren't given any information about our products, when we get to the change part, we could safely assume that probably the reaction is going to head towards the product side, which means on our reactant side, this would be minus X. This would be plus X, just like we did before. Again, all the coefficients here are 1, which is why they're all X's. And then we would drop in our equilibrium by carrying everybody down. Any questions on the ice table so far here? So just like in the previous chapter there, we got all of our equilibrium. We're going to go into our expression here and basically solve for X. So if we do that, that will get us X squared divided by 0.5 minus X is equal to 7.1 times 10 to the minus 4. So as we talked about previously, because our K value or Ka value is relatively small, we can go and try to do an assumption. So we could assume that X is equal to 0. Remember, when we do that, we cannot get rid of all the x's that are there. We can only get rid of, obviously, the x's that we're going to subtract something from. So in this case, it would be this x right here we would want to get rid of. So that would reduce us down to x squared over 0.5 is equal to 7.1 times 10 to the minus 4. We're going to multiply the 0.5 to the other side, do a little square root action there, and it looks like we will end up with, after you take the square root, we'll go with an x value of 0.019. Remember, though, that when we do make that assumption, we do want to make sure that it is okay. And for our class, we are going to be using that 5% rule. So to check it, we want to take the x value we got. We want to divide it by what we were going to subtract it from, which was 0.5. And we want to times it by 100%. And I hope it's good. Looks like it is. And we got something like 3.7%. And that means that the check is good here in this particular case. That means that that would be our x value. And in this particular case, remember that it is really H plus that we are looking to try to get. Maybe if it freeze up, there we go. I think it's coming back up. The pH would equal minus the log of the H plus concentration. And if we do that, minus the log of 0.019, and that's going to get us a pH of 1.72 in this particular case. And in that particular case, that obviously is acidic and is what we would expect it to be. Any questions on any of that there?
Yeah, how did you know that the check, when you checked it, how did you know that it was good? Like,
Yeah,
yeah,
we
how do
use
you know if
the
it's good or bad?
we're going to use in this class, like we talked about, what is sometimes referred to as the 5% rule. So the 5% rule is what we're doing on this one. So we have 0.122 molar monoprotic acid. Again, they really didn't give you a formula or which acid specifically you're talking about. So again, here HA could be used as sort of a generic formula for an acid, and monoprotic again means it has one H. So we could set up our reaction here. Again, just going to kind of break apart. We have the Ka value given to us. So we're going to do our initial, which the only thing they gave us was this guy. So that means these guys will be 0. Change, again, we can assume it's going towards the product side. So minus x, and plus x, which means once we get down there to equilibrium, 0.122 minus x, and x. Any questions so far on the ice table there? Okay, just like before, we would put this into our Ka expression. We know it's a Ka expression because we do see H plus there on our product side, and that would get us our H plus, our A minus, and our HA, and that is going to equal our 5.7 times 10 to the minus 4. We're going to throw everything in there. It gets us x squared over 0.122 minus x is equal to 5.7 times 10 to the minus 4. We could assume that x is equal to 0. That would get us x squared over 0.122 is equal to 5.7 times 10 to the minus 4. And if you do that multiplication, and hopefully you did a little checking as well, you will see this is not so good. we would end up with an X value of something like 0.00834. We would check it by dividing it by what we were going to subtract it from, which is the 0.122 or 0.122, yep, times by 100. And in this particular case, we end up with like 6.8%, which means this is not so good, this assumption. So again, because it's above 5% here, we actually should not use the assumption. And you do need to now kind of go back and solve it, in our case, in this case, using the quadratic formula. First off, any questions on the ice table? How we know it's not no good? Any of those questions? So really, because it's no good, we pretty much need to back up to here and basically multiply everything to the other side, kind of combine everybody and go into our quadratic. So I'm just going to kind of flip the page here so I got somewhere to write. And that means if we multiply everything to the other side, that would get us x squared is equal to 0.122 times 5.7 to the minus 4. Gets us something like, we'll call it 6.95 times 10 to the minus 5. And then that's going to be minus 5.7 times 10 to the minus 4x. Bringing everybody to one side, x squared plus 5.7 times 10 to the minus 4x minus 6.95 times 10 to the minus 5 is equal to 0. That goes into our x is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. Kind of just putting the numbers in there. That gives us minus 5.7. My pen doesn't go crazy every 2 seconds here. Kind of clean up a little bit. 5.7 times 10 to the minus 4 plus or minus. If we kind of do the square root part and put our numbers in, we end up with 5.7 to the minus 4 squared minus 4 times a, which is 1, times c, which is minus 6.95 to the minus 5. I think gets us something like 0.000278. Do a little square root of that. 0.0167, we'll call it. 0.0167. That's going to all be divided by 2, it looks like. So I'm assuming minus 5.7 to the minus 4, doing the plus there, gets us 0.01668 divided by 2. Gets us an x value of 0.00806 as our x value. If we did the negative and the subtract, we obviously get a negative number, which would be no good. So, and you would get a negative number, which obviously would be no good in this particular case. That means that is our x value. And if we go back to our table, H plus equals x, which would equal 0.0806 molar. Now we're good to go into our pH, minus the log of 0.00806. And gets us something like a pH of 2.09, which is good because it is acidic and we're dealing with an acid, so that all makes sense. Any questions on where any of the numbers came from, why we did any of that stuff there? So again, really important to make sure that you do check your assumption. As you can see, will not work 100% of the time. So you definitely want to make sure that you do check them.
Professor?
Yes, sir.
I got 2.08. Is that okay?
Yeah, as long as you honestly, as long as you went through and we went through the quadratic, maybe with some different rounding, you might get a slightly different number. As long as you didn't use the assumption in this case, you'd be okay. Even, and this would be one of those cases where, again, if you use the assumption, you would get something similar, but it's not always the case. So again, as long as you did kind of not do the assumption in this case, or checked it and saw what was wrong and continued on a different way to get it, it should be okay with some rounding if you got to 2.08. Other questions? Okay. All right, so obviously weak acid problems, very similar to really ice table problems and equilibrium problems. Again, the major difference, as you can see here, is at the end, we're going to be looking for the pH. So ultimately, a lot of times we're looking for the H plus concentration. Any questions on that there? Okay, so we'll lay it up here for now. So what's going to happen is the quiz will start about 1 there. There's going to be a separate link, so everybody's clear. It's going to be a separate link for the quiz. So we'll say something like taking quiz 1 link. So that's where you want to go next.